So at this stage, I want to introduce Erik Alexanian. He's done some fantastic work related to radical chemistry as it relates to CH functionalization, getting really unusual site selectivity going against the normal trends of radical chemistry by using some really bulky reagents. And he's definitely one of the leaders in this type of application. So we're delighted to have you join us today. All yours, Erik.
Okay. All right, that should do it.
That's great.
Okay. First of all, Hugh, thanks so much for the invitation today. This is a really amazing seminar series, and it's a real pleasure to be able to talk to you about some of our work in hydrocarbon functionalization over the past 6 or 7 years or so. Before I forget, I'm a whiskey drinker, so definitely Jameson, not Guinness, but I've had plenty of Jameson since I've been out here. To get started, what really motivates us, I would say the most, thinking about CH bond functionalization is, really just how far behind nature we are when we think about possibilities. So, for instance, if nature wants to synthesize Taxol in a real beautiful series of selective steps, nature is able to produce that. It's 8 different hydroxylations with oxidation states controlled along the way. And for synthetic chemists to think about doing anything like that right now, it's sort of science fiction. These are really difficult reactions to do selectively. Another reaction that nature has no problem with is CH bond halogenation. So for instance, here with this alloisoleucine derivative, if nature wants to do a primary CH bond chlorination, it's not a problem. So this alpha-ketoglutarate dependent non-heme iron enzyme can do a primary selective CH chlorination, which is then followed by an enzymatic cyclization and taking on to carnitine. So, what the question that we really think about in our group is, how do we get anywhere near this level of site selectivity in CH bond functionalization? And our inspiration really came from some very classical chemistry. What I think, you might say is the first example of an aliphatic CH bond functionalization in synthesis. And that's the Hofmann-Leffler-Freytag reaction. So this uses a reactive heteroatom-centered radical. Okay, so starting from a bromoamine, there's a protonation, an NBR bond homolysis, followed by a 1,5 H atom abstraction and cyclization to the product there. So that's a very classical reaction, of course. Another really historic reaction was Barton's nitrite ester photolysis. So in this example, used to make aldosterone acetate from an oxygen-centered radical formed from that nitrite photolysis. But of course, in both of these reactions, the hydrogen atom transfer is a 1,5 process. So it enjoys that sort of kinetic selectivity. And that's, very widely understood. And what we thought about in the group is, how do we potentially think about doing these types of reactions, but in an intermolecular setting? And I think if we think about these reactive heteroatom-centered radicals, how are they going to be selective in these reactions, right? They're highly reactive. How are we going to be able to choose between different CH bonds in organic compounds? It seemed like a really big challenge. Now, it turns out that if you tune the radical appropriately, you can really get some amazing reactivity. So what we've focused on are amidyl radicals, okay? So these are bulky amidyl radicals. So there's an N-tert butyl group here. First of all, these are very easily prepared from amide, so that's great. So they're very convenient to use. And the important thing is that the parent NH bond is about 110 kcals per mole. So aliphatic CH transfers are going to be exergonic pretty much in all cases. And I'll also show you that you can get some really good site selectivity using these reagents. So we started by looking at CH bond halogenation, and this is a few years ago. I won't talk about it too much today. But we're able to functionalize a number of different compounds. We started with the bromination. So here's an example of a memantine derivative, site selective for that tertiary position. Later on, we developed a CH chlorination, and this was with my friend Chris Vanderwall at Irvine. So this reaction was used actually in the first step of the synthesis of chlorolysoclamide. So we took scalariolide, which is commercially available, and then using this chloroamide, and you could run this on 10 to 20 gram scale. It's a very easy reaction to run with just a little radical initiator. That chlorinated product was then taken on in a few steps to the natural product. And one other thing I'll point out, in all of these reactions, we use substrate as limiting reagent. So we don't have excess starting material. We don't recycle our unreacted starting material. These are all a single pass, single reaction yields. And as Hugh mentioned in the introduction, we've also started to look at getting really interesting site selectivity. I think this is one of the major areas in CH functionalization going forward, is really trying to get either catalyst controlled site selectivity or reagent dictated site selectivity. And here's just one example using artemisinin as substrate. So what we did here is we moved those CF3 groups over to the ortho positions, and what that does, it makes a much more hindered nitrogen-centered radical after that NCl bond cleavage, and now we can actually get primary site selectivity, which hadn't been done before with chemical reagents. Now it's not perfect selectivity; we have a ways to go, but it's a good start and a good proof of principle, I think. One thing I'll mention: these are really easy reagents to make. So here I show you over 10 grams of the chloroamide from that artemisinin reaction. So you can really make as much of this reagent as you would want. Very easy to do. Okay, so after our halogenation chemistry, we got to a point where we wondered what was the next thing to do. And in terms of reactions, there might be 10 different groups you would want to introduce into a hydrocarbon. And instead of developing 10 different reactions, we really wanted to make one reaction that could serve as sort of a platform for other CH functionalizations. And we always kept coming back to alkyl xanthates. These are very easily transformed via radical reactions and polar reactions, and I'll show you some examples of that in a minute. And the way we did that is with a xantholamide. So shown here in the blue box. This is a yellow powder. Okay, now it's commercially available from Sigma. You can synthesize this from the chloroamide very easily with potassium ethyl xanthate. And using some blue lights, you initiate the radical chain. You make the nitrogen-centered radical, which then does the CH bond abstraction and chain transfer of the xanthate. Okay, so I won't show too many different examples here. This is work from a couple years ago, but we could functionalize natural products. And once again, we're going to functionalize the most electron-rich, sterically accessible site. So with androstenedione, it's the B-ring methylene shown there. And probably my favorite example in that paper was the functionalization of longiphelines. So that alkene can be pretty problematic. So if you use something like a high valent metal oxo, it's prone to oxidation chemistry, can do other reactions. But using our reagents, we oftentimes can get CH functionalization with things like alkenes present in the molecule. And this reaction actually worked best neat, so no solvent. So it's a radical chain process, and you'd think higher concentration is better. But you take that longipheline liquid, you put the yellow powder on it, shine blue lights, it sort of warms up, and you get 4% yield of this single product, where the hydrogen atom transfer occurred away from the quaternary centers at that accessible methylene site on the medium ring. So just very briefly, you can take the xanthate group and do quite a number of different things with this. This is beautiful work from groups like Samir Zard, Philippe Renaud, and others. So we can transform that xanthate to a vinyl group. You can do a CH amination via some polar chemistry, transform it to deuterium. One reaction we had to develop in that paper was the transformation of a xanthate to a hydroxyl group. And this is an interesting transformation because the perfect chemoselectivity of the overall process. So oftentimes CH hydroxylation can be problematic. You'll get overoxidation to the ketone. But in this case, that's controlled by the workup condition. So with zinc, we get the hydroxylation. With MCPBA, you go chemoselectively to the ketone. We can also do trifluoromethylthioylation. And probably the simplest reaction is just to work this up with an amine, and you cleave off that xanthate group. And you take the thiol, you can do things like bioconjugation by a thiolene click chemistry. And actually it was surprising to me that the transformation of a CH bond to a thiol hadn't been done before. Okay. So switching gears just a little bit, I wanted to talk about sort of a new direction for our xantholamide chemistry. And that's in functionalizing polymers. So typically, the way this is done is using peroxide. So those will favor functionalization at tertiary positions. Okay, so in a branched polyolefin, that's going to be followed by degradation. That's usually will happen before you get addition of something like your maleic anhydride that you have in the reaction. And what we wonder is if we could use the sterically based site selectivity of our reagents to move away from that tertiary CH site, functionalize commodity polyolefins, and then do some very interesting reactions with those sorts of products. And this work was is in collaboration with Professor Frank Leifarth, my colleague at UNC. So this was published last year, and I won't spend too much time on it, but the sort of reactions that we would run is taking things like polyethylethylene and our xantholamide. You shine blue light on this, and you get a good amount of functionalization on that polymer. You can tune the amount of functionalization based on the amount of reagent that you add in. And what was an important result for us moving forward and thinking more about direct application of this, you can run the reaction with no solvent. So once again, you run it right onto the polymer and you get a good amount of xanthylation. One thing I'll point out is when you're functionalizing a polymer, you don't need that much functionalization for the reaction to be very useful. So even 4% is plenty. Okay. So recently, thinking more about commodity polyolefin functionalization, the way that you want to do this, especially in industry, is using something very different than our normal round bottom flask. So the way they like to do this is via reactive extrusion, where basically the solids are put onto this hot metal screw. It turns the reagents and then out comes the polymer. And this actually works with the xantholamide. And here's some pictures of what those instruments look like. So as you can see here, this is the functionalized isotactic polypropylene. You can see the peaks in the proton NMR shown here. This is the GPC analysis of the reaction. So what's really important is that these peaks look the same. So one of these is just the isotactic polypropylene extruded. And then our functionalized compound is that maroon peak, and you can see that the molecular weight distributions are still very similar. And looking at actual pictures of the compounds, on the left here is the extruded polypropylene. The xantholylated polypropylene has that sort of yellow tinge. This is 1% functionalized, and actually it now changes the physical properties of the polymer pretty significantly. So the functionalized polymer now adheres to glass twice as strongly as the simple polypropylene does. So that's a nice proof of principle. We're really excited about different applications of this in the future. So thinking more about small molecule functionalization and the future of trying to use these heteroatom-centered radicals, we started to think about moving beyond chain mechanisms. These are great for transferring certain functional groups, but there's always going to be some potential reactions that you might want to run that would be pretty difficult to be able to run these in a chain process. So we started to think a lot more about trying to do catalytic reactions. And our first work in this area was in collaboration with my colleague, Dave Nasevich. And we developed this acridinium catalyzed CH bond functionalization shown here. So this is also using the commercially available acridinium catalyst, phosphate base, and hexafluoroisopropanol. Okay, the first reaction here that I'm going to show is the azidation. So this works with completely unactivated CH bonds. This reaction actually favors tertiary sites, so it's complementary to our chain chemistry. We can also apply this to more complex molecules as well. Okay, and what's really exciting about this approach, I think, is you can change the reaction products just by changing the trap. Okay, so this is sort of a nice platform reaction where you can access azidation products with sulfonyl azides, CH fluorination, bromination, chlorination. You can add in an activated alkene and get an alkylation product. You could also do trifluoromethylthioylation as well. So here are some examples of the sorts of things that you can do with that system. Just briefly talking about the mechanism here, we believe that this is oxidation of the phosphate base. So the excited state of the acridinium is a fairly strong oxidant. It's over 2 volts. And we think that's strong enough to oxidize the phosphate base to make an oxygen-centered radical, which then does a CH bond abstraction followed by addition to whatever your radical trap is, and final electron transfer to close the catalytic cycle. Okay, so getting back to nitrogen-centered radicals. So, we always had this dream to be able to do amidyl radical chemistry catalytically. And, our thoughts in this area just kept coming back to the idea of doing proton-coupled electron transfer. And, the beautiful work from Rob Knowles' group has shown just how powerful this can be in synthesis. And the idea was, well, maybe we could use a simple amide and now form the amidyl radical under mild conditions. And, we started to play around in this area, and then Rob Knowles and Tom Rovas at about the same time published an excellent intramolecular version of the sort of reaction we were thinking about. And those are both shown here. So in this case, it's a P set to form the nitrogen-centered radical. You get a 1,5 H atom transfer followed by addition to the trap. And actually in Rob's paper, he reported an initial intermolecular result using 10 equivalents of substrate. So good proof of principle. Rob knew about our work trying to do intermolecular chemistry. We knew about these studies, and then we decided to form a team and collaborate and try to develop a general way of doing this sort of chemistry intermolecularly. So one of the first reactions that we tried to do is shown here. So it's a simple alkylation of THF using bisulfonyl ethylene. So we have our iridium catalyst and our base in here. And the first thing we tried was using a sulfonamide. So could we form a nitrogen-centered radical here? That NH bond is still around 103 kcals per mole. And see if we could use this to trap an alkene and deliver the CH alkylation product. And we were excited that even some of the first results, first reactions we ran gave good results. So with one equivalent of that sulfonamide, we got a 75% yield of product. So a good start. Now, if the nitrogen-centered radical abstracts the CH, you regenerate the sulfonamide. So there's no reason you would need a full equivalent. So we started to use less and less. And the reaction yields don't drop that much. So what's the next experiment? Take the sulfonamide away, and you still get plenty of product. So it's pretty clear the sulfonamide's not doing anything in the reaction. And actually, if you lower the amount of iridium, the yield goes up even further. So the bottom line here is that the sulfonamide isn't doing anything in the reaction. So just briefly, I'll discuss the substrate scope. So we can functionalize completely unactivated aliphatic CH bonds, different heterocycles shown here. This works really well at benzylic sites. And we can use a number of different olefins to trap. So it's not limited to bisulfonyl ethylene. Here are a few different ones shown here. It just has to be an activated alkene for that trapping step. And we've also started to apply this to more complex molecules. So here's an alkylation of the activated position here in ambroxide. Here's our memantine derivative again. We get good selectivity with benzylic, between different benzylic sites as shown here. So with ibuprofen, we get a single product. And with this pyrimidine containing compound, we also get a single benzylic functionalization. So the real question for us was, what is the mechanism of the reaction? So initially we thought, well, maybe we're forming some small amount of radical, and this is just a simple chain process where the catalyst isn't doing anything at all. So we tried to do some control experiments where you add in radical initiators. We didn't see any product. And the more straightforward experiment is to measure the quantum yield. The quantum yield of the reaction is very low, so it's just not consistent at all with the chain process. You take away the iridium, you get no product. You take away the phosphate base, you also get no product. So if we compare the site selectivity of this alkylation to the selectivity using the acridinium system, so the work that the Nisevich group did with us, the site selectivities are very different. So with the acridinium, if this is a phosphate oxidation and you get a one-to-one mixture of products here, and with this iridium phosphate system, you only see a single product. It's just not consistent with phosphate oxidation playing a major role in this iridium chemistry. So what sort of led us down the ultimate path to getting to where we are today, we thought a lot about this interesting coordination of the iridium catalyst and the phosphate base. So Rob's group had shown this previously. The phosphate base coordinates to the CH bonds in that ligand system. Those are relatively acidic sites. You can see with this NMR titration, the movement of that peak, and you can pull out an equilibrium constant, which is about 1 × 10⁴. So this is a strong coordination between the phosphate and the catalyst. The job plot also indicates that this is a 1-to-1 coordination of the phosphate base and the catalyst. And Rob's group actually obtained this beautiful crystal structure of the iridium system bound to the phosphate base, and you can see the interaction right here. So nice evidence of that coordination as well. Okay, so this is just another one of the standard reactions that we looked at. And, you know, we started to question if that CH bond interaction is so important to this chemistry, what if we replace CH with CF? Very similar size, would completely disrupt this coordination. So if that's the case, we should make the fluorinated catalyst and the reaction should totally shut off. And that's what we see. A major difference between these two catalysts. And then just to make sure that we didn't synthesize some really poor catalysts. We applied it to one of the many reactions from the Knowles group, showing how useful these catalysts can be, and the fluorinated catalyst worked just fine in this cyclization reaction. So it is an active catalyst for proton-coupled electron transfer, but just not in this particular system. Okay, so this is the last chemistry slide, and it summarizes quite a bit of work. So it took us about a year to really get a handle on what we think is going on in the reaction. So what we ended up doing is looking at some time-resolved photoluminescence as well as transient absorption spectroscopy to try to see what's happening when the excited state of the catalyst is quenched. So over here on the left, what this shows is that without phosphate and without substrate, the iridium-3 does not form iridium-2. So that would be the sort of green and blue and purple line here down at the bottom. So this, in the y-axis here, shows increasing iridium-2 concentration. However, when the iridium is in there with the base and the substrate, so ethylbenzene was just a representative substrate here, that's when you start to see iridium-2. So it requires your CH substrate to be in there in order to see the iridium-2. And then with more substrate, you see even more iridium-2. And then to prove that this, or to get some good evidence that that CH bond cleavage is involved directly in the electron transfer, we looked at ethylbenzene and deuteroethylbenzene using some time-resolved photoluminescence studies. And you can see here that there's a quenching KIE. So the quenching of the excited state involves that CH bond cleavage step directly in the electron transfer event. Okay, so our best mechanistic hypothesis at this point is that this complex is excited to give a photoexcited complex, which then participates in a CH bond p-set reaction. Okay. So typically, proton-coupled electron transfer uses relatively acidic bonds, such as NH bonds, right? Where the base can bind. There's no way that the phosphate base is going to bind to a CH bond, especially not in an intermolecular way at any appreciable amount. But we think it's because this complex forms and you can bind to that CH bond as the electron moves, that this is basically a CH p-set reaction. And we think this is potentially a new elementary step for CH bond abstraction. That's then followed by addition to the alkene and electron transfer, proton transfer to get to the product. So we're really excited about this reactivity. There's a lot of different directions. We're taking this synthetically. There's also a lot of questions that we're still trying to answer going forward as well about mechanism and other things like that. But really exciting stuff and very unexpected when we started the project for sure. Okay, all that's left for me to do is to thank my group. I've really been blessed with an amazing group of coworkers at UNC. I've listed the students that have been responsible sort of throughout the talk. Also, Frank, Leifart's group, it's really been an excellent collaboration starting our polymer work there, and it's also been an amazing time working with Rob over at Princeton and his group. And there's a lot of really interesting results that those collaborations have led us to, and that's been a lot of fun. So I'll stop there. I'm happy to answer any questions. And once again, Hugh, thanks so much for the invitation today.
Erik, wonderful talk. Time's running a bit late, so I just want to make one comment. It's amazing that last part of your work where you've got that new mechanism for the photoredox possibility for CH functionalization. I think that's a fantastic results. Congratulations on that. That can develop very, very nicely. Thank you. I also want to congratulate you on how you've demonstrated the importance of collaborative research, because obviously, you know, you had a fantastic foundation in what you were doing in radical induced CH functionalization, but you demonstrate the ability to collaborate beyond that with other synthetic organic chemists, and that's really a fantastic accomplishment as well.
Yeah.
Something that we strive for in the center, but you're clearly doing it yourselves. Well done.
Yeah, thank you so much. Yeah, absolutely. It's so much of this work never would have been possible without Frank and his group, as well as Rob and his group. It's been a real pleasure. And it just makes chemistry a lot more fun and exciting, I think, too.
We couldn't agree more with you. Okay, thanks very much.